Ka tangi te titi, ka tangi te kaka, ka tangi hoki a hao, ti he Māori ora. E na mana, e na reo, e ora rakatira mā, tēnā koutou, tēnā koutou, tēnā koutou katoa. Tēnei kātu e raro e te maru o ka mana whenua, ka te māmoe waitaha kaitahu, no mai hara mai welcome. I stand here under the cloak of the people of this place, ka te māmoe waitaha and kaitahu, and welcome you here. Ki te whare, tūnei, tēnā koe, tū tonu. And to the house that stands here, greetings, may you stand forever. If there's any question about where we are standing forever and there's an earthquake, you know what to do, drop, cover and hold. If there's threat of fire or other emergencies, then exits are out here and we'll meet in front of the archways. E te mate haere hoki atu rā ki te po. And to those that have passed, may we remember you as you pass to the other side. And just personally, I'd like to make an acknowledgement to my PhD supervisor who passed away within the last month and was farewelled in the UK, Professor Haroon Ahmed, a great mentor and guide to me in my career. So may we all remember him here in this time. Ko waio, no o te poti ahau, ko katarani te iwi, hei kaimahi aha te wharewananga o tako whakaihuaka, ko Richard Blakey taka wingua. Greetings everyone, I'm Richard Blakey, Deputy Vice-Chancellor, Research and Enterprise, and it's my great privilege to be hosting this inaugural professorial lecture where we celebrate the promotion to Professor for Ivan Sammut in the Department of Pharmacology and Toxicology. It's a great occasion and there's many people to greet and welcome. We have unfortunately a depleted academic party due to illness largely, the number of things that are going around now that we're all relaxed with the end of lectures. It seems to be catching up on a few people. So there are apologies from Dean of Biomedical Sciences, Professor Lisa Matusu-Smith, and the Pro-Vice Chancellor Division of Health Sciences, Megan Gibbons, who both give their apologies. But we do have many special guests in your whānau, friends, family and members of the Dunedin community to welcome. I'd like to particularly acknowledge your wife, Janine here, and your daughter, Laura, who are here and present. I think your son may be going to watch this in the future. And I think there are many people gathered worldwide from South Africa to the UK, the US and other places who are joining us either live online or are watching this at some point in the future. So no mai haramai welcome to you all. My role is to give a brief introduction to the event, say a couple of words, but I'll hand over to Professor Catherine Day, who will introduce Ivan's IPL. We'll then have the IPL, a little bit of a vote of thanks, and then get to the staff club for some drinks. Apologies to those who are online who won't be able to join that. Hopefully you've got some refreshments at hand that you can enjoy. Promotion to professor is a big deal at the University of Otago, as it is in any major research-led university, and we like to celebrate that by inviting the promoted professor to profess to their community about the things and the people that have brought them to that place. Promotion requires sustained, outstanding leadership and performance across the three main areas of academic life, across teaching, research and service. And in Ivan, we have seen that demonstrated to a high degree, and you'll see that reflected tonight. In particular, I'm very inspired by some of the things that Ivan does in his own words, in work that straddles basic sciences through to clinical research and application. That commitment to teaching and teaching students to go on to successful careers, planning that careers in academia are as equally valued as careers in clinical practice as in commercial research or translation, really exemplifies the kind of work that should be happening with people in disciplines that have outcomes for people at their heart. The collaborative nature of your research and your engagement with postgraduate research is also exemplified. The fact that you work with some of our leading chemists here, and I notice some of our chemists in the audience, people like Dave Larson, but also through national networks, people like Dame Margaret Brimble is notable. The fact that you connect with leading clinicians, and I see some of those here in the work in your work around cardiovascular and renal issues, and did I see a late arrival from Rob Walker. So some of your great collaborators are here. So look, without further ado, please accept our most heartfelt congratulations on behalf of the University for this most well-deserved promotion. And I'd now like to invite Professor Catherine Day to give a more detailed introduction to your lecture. Thank you very much.
Is that right? Yes, so tēnā koutou katoa, good evening and welcome. I'm Catherine Day, the Deputy Dean, and as Richard has already indicated, Lisa sends her apologies, sincere apologies in fact, because she texted me very early this morning at 6 o'clock. I don't know if she's sick. Why is she texting me at 6 o'clock to say she's unwell? Anyway, so it's my pleasure to provide a brief introduction. I think I'll cover some of the same territory and points that Richard's highlighted, but also a few other things. So firstly, we are very lucky to have Ivan as a member of the Otago community, where he's made really a number of significant contributions in all spheres of what we would expect for an academic. So Ivan hails from the UK, and I think he completed his undergraduate studies at the University of Sunderland, followed by a PhD, and I managed to find the title, which is Acyl Compounds, Endogenous Modifiers of Intracellular Myocardial Function. So I think that was the start of a translational research journey, which has continued on till now. Following his PhD, he moved to London, and he had 8 years at the Royal Brompton and Harefield Hospitals at the National Heart and Lung Institute, which is part of Imperial College of London. I think I've got that all right. It seems quite a mouthful of a place. And he was there first as a postdoctoral fellow and then as a research scientist, and all the time focusing on clinical management. And I think this time really sort of established Ivan's long-standing research and interest in cardio-preventive interventions that I think we'll really hear a lot more tonight. So that's the foundation of the research that followed. And so in 2001, Ivan came to Otago, and he's really contributed right across research, teaching, administration since then. And as we expect for someone who's been promoted to professor, he's published widely with more than 50 publications. But he's also secured patents for his research. And some people at Otago I know have struggled to do this. So this is really a good achievement of Ivan's and should be congratulated. And his main patent is now been granted full status in the US and in Europe and in Australia with third-party take-up. So that's quite a significant achievement, and so Ivan should certainly be congratulated for that. And so at the... well, there we go. Why not? Indeed. So Ivan's highly collaborative, and we've already heard that from Richard, with multiple groups involved. And I think we especially want to mention Heart Otago and the value of supporting networks that really make a difference to people's research lives and be part of a community. And so Heart Otago has been a good part of and sort of a home for some of Ivan's work. And I guess I also wanted to note that Ivan has had a number of students, and he's had 3 students, PhD students, get exceptional theses. That's really quite an achievement, and again, I think it speaks to the inspiration and encouragement that Ivan provides to students. So it's really done a great job with student supervision and mentoring. So all this research takes money. We all know that we require money to do things, and Ivan's had a strong record of funding with success in both HRC, Marsden Fund and MB, so as well as a number of other foundational grants which have, I think, secured the path through, which we might hear more about. Lastly, I just want to touch on teaching. Ivan's a great teacher. He's passionate about ensuring courses run well, and he's had a number of leadership roles. And so particularly in the med program, where he convened or still convenes the respiratory block in ELM2, and that block has been voted the top block several times. So I think that, again, getting awards from the med students is, again, not easy, so well done. And he's also, for I think 5 years, been Associate Dean Medicine for Biomedical Sciences. So that's a significant role, taking on leadership roles for the school, and involves lots of committees, lots of long meetings. So we thank Ivan for his service as Associate Dean Med, and I know he's passed the baton on with that now. Again, I guess Ivan also has had significant roles within pharmacology and providing a leadership role in pharmacology. So lots of service, but outside, he's, as well as service beyond his department, Ivan's been a great servant to his department, being deputy head of department for a number of years, and now being the head of Department of Pharmacology. So he's been busy and doing lots of the activities that are required for the functioning of a university. So please join me in welcoming Professor Ivan Sammut to give his inaugural professorial lecture, which is entitled Drugs for the Broken-Hearted, Developing New Therapeutic Agents for Heart Disease. Thank you, Ivan.
Thank you, Catherine. Thank you, Richard. And with that, I think we should finish and go home now. There's not very much I can say. Tēnā koutou, tēnā koutou, tēnā koutou katoa. Ko Ivan Sammut, ko toku ingoa, nau mai, haere mai. So welcome. Thank you all for coming here tonight. I'm amazed. There's so many familiar faces, colleagues that I appreciate work you've done, the support you've given. Let me start off by saying thank you to Joanne, my wife, who is also my collaborator in so many of these papers. Thank you for coming here. My daughter Joanne, and as Richard said, my son is unfortunately away, but he can make up for it later on. So let me start off by giving you an idea of where we're at. Okay, so to all those colleagues who work in medicine, this is going to sound very familiar, so I do apologize if I'm going to bore you, but it all started with a heart. Sorry, Rob, not a kidney, but a heart. It's just a mere pump that pushes blood around the body, right, and through the kidneys. Well, this is my grandfather's heart. To be accurate, this is a heart model that stood on my grandfather's desk, and when I was a child, I used to go in and look at these models, and gosh, it kind of reminds me of this every time I go into the anatomy museum, same sort of display. So I used to ask a lot of questions about how these worked. You know, most kids would play with Lego. I kind of had this fascination with things like this as well. I wanted to see how things, you know, worked, nuts and bolts. And then I went and ruined it all. I had a few ideas about what experiments should look like, so I devised my own, one of which surrounded this creature over here, which happened to be sitting on my desk and with an intact stinger. So I, being this 10-year-old child, nasty piece of work, took the sac and stinger out and then wondered if, and this was my hypothesis, would it work if I reapplied it into a volunteer? Luckily, my brother was standing by, and completely unexpecting what happened next, I took a pair of forceps that, you know, because we were a medical family, forceps were around the place, right? So I took a pair of forceps and injected the stinger into him. Lo and behold, not unsurprisingly perhaps, the poison worked, it did produce a massive histaminergic response. And I learned two things. One is if you took the stinger out of a wasp, you could produce a pharmacological response in your subject. And the second one was the importance of getting prior informed consent. My father gave me that. Okay, so at that stage, my father was in, we were in King's Lynn, and he moved to the Royal in Leicester as an obstetrician. Of course, my mother was slightly overwhelmed with these two boys. So not unsurprisingly, we were sent to a boarding school. So, and my brother never forgot that. But so yeah, showing right picture over here. So we were on the border of the smallest county in England, Rutland. It's a beautiful place. Well, I think it is. It's famous for quite a few things. Ratcliffe was a formative experience for me in that we had a lot of sports, perhaps not so academically demanding, but a lot of sports, and that I enjoyed as a boy growing up. So there's Rutland. You can see it in the red dotted line. There's a big water park in the middle. Well, actually, it's a lake with some sunken villages. And it's famous for a few things. So if you think of Melton Mowbray pork pies, the proper ones come from Melton, and there is one shop that serves these, and this was Christmas tradition. Also a few other Christmas traditions, Stilton cheese and Ruddles beer when I got older, obviously when I got older. But, and the other thing that surprised a lot of tourists to the town was the size of our horses. We had, this is Oakham Great Hall, and there's all these tributes provided by nobles and so on, and they're hung on the hall walls, and they go right up to the present day. No horses were involved, but it's a good trick to play on tourists as they come into town. So, as Richard and Catherine said, I then basically was looking at a choice of careers, and I had some thoughts, but eventually I settled on pharmacology. Now, my father, 3 generations of clinicians, want to tell me different, and so did my father's friends. Why would you pick pharmacology? Okay, it is the hardest course going, right? Most medical students fail pharmacology. Don't you dare do that, right? So it was something that I wanted to prove I was capable of doing and excel at, and so I went to the University of Sunderland. And at that point, I met, after I'd done my degree, I met this gentleman over here, Professor Mike Spedding. He's a major calcium signaling player, was at the time. And I'll talk about my research in a second, but effectively I did my degree, did my honors in opioid research, and then spent a research internship at Stockton Hospital looking at prothrombin times. I was there to study, probably quite early on, the impact of liver injury and drugs and health on prothrombin times and INR. So with warfarin, quite interesting to me at the time. I also had the free reign of the pathology department, so that was enjoyable. I got invited to attend postmortems and surgical procedures, and gained a lot of experience, and it stood me well. My research began in my PhD with this idea that lipid metabolites, and Regis, you know this, can build up. So you got these inhibition of beta oxidation when hearts are denied oxygen in ischemia. You get a build-up of these metabolites, and they can impact the heart. So you know that mitochondria damaged in hearts subjected to ischemia perfusion. So I spent a good deal of my time trying to replicate that injury in mitochondria. So I isolated these almost intact mitochondria and then subjected them to high levels of calcium and to lipid metabolites. Spent a lot of time down looking at electron micrographs. Okay, so nearly ruined my eyesight, but there you go. We got these mitochondria that look like the ones in the pictures above in the intact hearts. So yes, calcium and lipid metabolites were all responsible for some of that damage, but also what I discovered was that if you use cyclosporin A, the immunosuppressant, you could also block what was then called the mitochondrial pore, this non-specific pore that was sitting on the in a membrane of mitochondria. And if you load the mitochondria with calcium, they would absorb it, and then it would be released eventually. But if you put cyclosporin A, it prolonged it. And then the addition of palmitoyl-CoA, in this case, one of the lipid metabolites, actually promoted an earlier opening of the pore and faster release with higher concentrations. And that's reflected in this diagram over here, where you've got palmitoyl-CoA over here producing a rapid release of calcium. But if you add the bupivacaine, which is a local anesthetic, or cyclosporin A, you stretch that time out. So cyclosporin A was effectively slowing down the release of calcium. So 3 years of hard work, and it boiled down to this diagram over here, where oxidative stress promoted pore opening. If we used lipid metabolites, we would increase the rate of pore opening. If, on the other hand, you added cyclosporin A over here, that would bind to cyclophilin and prevent the cyclophilin binding to the pore. So you prevented calcium release or slowed it down. So that was interesting in itself. That pore eventually became known as the mitochondrial permeability transition pore, which is now in every textbook. And people like Crompton and so on made quite a lot of noise about it. It's certainly valuable. One of my colleagues, Derek Yellen and Derek Hossenloy, had gone on to trial using cyclosporin as a conditioning agent to protect hearts in advance of ischemic injury. And they got a lot of success, but unfortunately, cyclosporin has a one-trick effect. So I'm going to try and show you something else. At the end of my PhD, I met this lady over here, Joanne, who's sitting in front. And 6 months later, I left. I went down to London. Sorry, Joanne. I do apologize. But she did try and find ways to kill me in the process. So this is us whitewater rafting on the Zambezi, just below Vic Falls. Yes, we did silly things then. I still do silly things, right, Katrin? I can't tell you how many grade 5 rapids are on that, but we went down it with a skilled helmsman. And the pair of legs sitting over there, or rather standing out there, that's Joanne, okay? Right. There's me just about to go in. We capsized at least twice on that journey. Amazing place. If you stayed in the white water, you're fine. If you were in the still water, the crocodiles. So just a point for anybody trying to do this in future. So I also got this position at the Northwick Park Institute for Medical Research, and this was to look at organ transplantation. Barry Fuller, Tim Bates, and Colin Green were my mentors. Colin was the director of the institute. It became the Griffin Institute, and the job over there was to look at organ preservation. How damaged do kidneys or livers become as a consequence of cold storage, and trying to improve the outcomes in that by adjusting those times. So, and I'll be brief about this because we did publish quite a few papers, mostly in mitochondria, but amongst my other techniques, I had to learn how to transplant kidneys and livers in rats And as you can see, my sewing had to be extremely refined. I still can't sew a button properly, saved my life, but I could do this. And you can see in this blood, this field without any blood in it, there's a renal artery and renal vein over there, and they're both anastomose. And anastomosing the ureter, I relied on Sandra to do. In fact, most of this work was done by Sandra, who also taught these microsurgical courses for house officers and house surgeons in London. So we also did other things as well. And in fact, I was involved with work at Raft, Restoration and Function, and also with the Blonde Mackindoe Institute. And I didn't realize at the time that the Mackindoe Institute was named after Archie Mackindoe, a Kiwi. So that's my first shot at it, okay? So we did cardiomyoplasty, which is in lay terms, a muscle wrap, a heart wrap. We took the latissimus dorsi muscle and used it as a pedicle and put it around the heart, wrapped it around, put clenbuterol into these animals to increase the force of contraction and use it as a ventricular assist device, okay? Put a pacemaker on it and it worked, but it's not ideal and there are better things out now. So that was something that we did work on. We also worked on monitoring pedicle grafts in facial reconstruction surgery and in breast reconstruction. So I had quite a lot of patient time in terms of monitoring revascularization. We also did some ischemic cardioprotection work in rats and in sheep models. And by the way, this is the surgical theater. This is a large animal surgical theater that served us very well. So it's well equipped. We need to work on this. Thanks. Right. So I then finished off my work over there with this paper, which was the first real involvement in carbon monoxide. And as you can see, we looked at ways to increase carbon monoxide release in animals, but also in tissue. So this was done specifically in aorta. We induce the enzyme hemoxygenase, which produces carbon monoxide. Yes, we do produce carbon monoxide. It isn't just there to kill people. We then looked at the vasodilatory effects, and this team of many people went on to produce molecular evidence, supported histology, and so on. Just to let you know, James Clark is head of physiology at King's College London, and David Axon and Martin Veasley are quite senior specialist surgeons in plastic surgery and general surgery. And I really enjoyed my time with them, and they stay my friends. So I had discovered that carbon monoxide produced this guanylate cyclase, induced vasodilation, but it's gone on since there. Let me put it this way. I arrogantly, Richard, you mentioned Nature. I arrogantly submitted this paper to Nature first, and they said, don't be stupid. Carbon monoxide can't be a vasodilator. It's toxic. It kills people, right? So we rewrote it slightly, put it into the British Journal of Pharmacology. Jane Mitchell snapped it up. The title appears on the front cover of the journal. It's had over 340 citations, so not bad for a toxic chemical. It's also one we describe as the Swiss Army knife of signaling molecules, because it has so many different effects. So moving on quickly from there, or not. Yeah, there we go. So then my next move was to the National Heart and Lung Institute at the Royal Brompton and Harefield Hospital. So I had a number of different roles over here. But the person over here is Professor Sir Magdi Yacoub, who at that time was the foremost heart-lung transplant surgeon pretty much in the world. And he still has my respect for all the work he did. So he interviewed me for the position at 2 o'clock in the morning, okay, between lists. That was the only time he had available, and he continued to see me between lists, and that generally meant the wee hours in the morning, because that's when most transplant work tends to be done. That's when most donor hearts and lungs become available. So Magdi was a pretty formidable character. He demanded that all his staff met his same very stringent qualities. This is Ken Suzuki, who was a cardiothoracic surgeon turned researcher at the time. Ken had come from Osaka. He's now a professor at the William Harvey Institute, and Ryszard Smolensky, who I worked with as well, and the two appeared on a lot of my papers. So we published in journals like Circulation, the American Journal of Pathology, in more circulation journals, and I really enjoyed my time over there. The other thing I'll point out is that this was pre-formative training. The model that Magdi encouraged was one that where researchers, scientists, and clinicians collaborated together, but also that we had this advanced postgraduate training for junior clinicians, okay, but also you can see any new scientific advances. Journal clubs serve to train clinicians. And my area was to bring in pharmacology to that, but also as a pharmacologist, I spent a lot of time on the wards providing teaching and support for staff, and also working with the teams. Found time to get married somewhere in all of this, so thank you, Joanne. Hope you're still happy with this. But one of the things Joanne did was point out she'd come to New Zealand in the early 1990s, 93, 92, yeah. And she'd missed out on coming down to Dunedin, and what she wanted to see was the albatross colony over here. So for some stupid reason, I said yes. Okay, so we came down, had a great time traveling around New Zealand. It's a beautiful place. In the late 1990s, this was 2000, we enjoyed ourselves, and I saw an advert. Having seen the Otago Medical School being signposted, then I also recognized that I'd read some of the papers from the Otago Medical School, okay, like Horace Merck and so on. Rob, you know these characters well. They were salient figures in our training, and I had applied, and strangely enough, I arrived over here. So two things. One is the Adams building was still there. I was promised when I came over for interview that it would be demolished in a short period of time. Didn't happen. I've got something at the end that might help this, but yes. So I was appointed a lecturer in pharmacology in 2001. And this gentleman over here was my mentor so this is David Clark. He was responsible for not just training me, but also bringing in the pharmacovigilance aspects that were profoundly important in the way drugs are administered, but also in terms of monitoring any adverse effects. So David kindled that interest in me, kindled an interest in teaching medicine over here. I took on the respiratory module in 2008, and then shortly after Cynthia, I took the both years of the pharmacology vertical module that became the clinical pharmacology module. In 2019, I was appointed as the Associate Dean, and I enjoyed my time over there. And Kurt, if I could possibly ask you to let me have it back, you can take over HOD pharmacology, that would be great. But I really enjoyed that teaching, that component. I still teach medicine is the prime area. So I became, mainly because I was late to a meeting, HOD pharmacology in 2024. So talk about research briefly as well, because there's so many people stank over here. In 2005, we published this paper, and this was largely due to the work of Rob Smith and Mike Murphy, he was at Cambridge at the time, having left biochemistry here. I'd actually struck Mike Murphy before at London as well, so it's a small world. And Joanne. And the other person over here is Vicky Adlam, who did the work as a PhD student, and Carolyn Porteous. And these people were responsible for taking MITO-Q, which is this coenzyme Q, basically tethered, so it's an antioxidant. It's tethered to a triphenylphosphonium group over here. And because there's a very high positive charge, it's sequestered into mitochondria. So as a consequence, you get accumulation of this antioxidant within the mitochondria. And if you subject the mitochondria to ischemia reperfusion, so we loaded this up in rats, took the hearts out, subjected them to a cessation of perfusion, so ischemia, and then reperfused afterwards, mimicking an acute myocardial ischemia reperfusion injury. Okay, we saw protection. So this is the before ischemia, and we use controls over here, MITO-Q treated animals, but also the individual components of the drug itself in isolation. As any good pharmacologist would do, we wanted to look at both negative and positive controls, and we had, pointer options. Yeah, we looked to see if we could protect the hearts. If you look at the white bars, MITO-Q actually increased the developed pressure in the hearts against the baseline controls. I'm sorry, I've just lost the pointer on this. I know Joanne keeps telling me never to fiddle with things, but I just did. There we go. Right, okay, so there's the white bars, and you get this increase. We also saw an increase in protection of the mitochondria, and it's, don't worry, I won't be asking questions later on, but if you've got ischemia reperfusion injury, like I showed you before, you've got this damage to the myocardium, the mitochondria swell up, so on. 14 days of prior treatment, if I recall correctly, resulted in no damage to the mitochondria, but when we exposed them to ischemia reperfusion injury, we had fairly good protection in those hearts, at least structure-wise. By the way, the MITO-Q was originally diluted in alcohol, and who would believe it? Rats don't behave like students. They don't like alcohol, so we had to find other things. Okay, so here's something that might startle you, and it's something that impressed us. This is from 2008. I've borrowed a diagram over here. So this is from Brilliance, and you can see that most patients fail to adhere to the drug medication, either because they don't like drugs, or because they have adverse effects that they don't like, or because they're not properly consulted in what the drug's going to do to them and why they need to take it. That's really important. So Rob's involved in this study. And by the way, I've seen papers now indicate 50 to 60% of patients fail to take the medication at 1 year. Right, so Rob was involved in this study, and we took a transgenic rat that we had that was hypertensive. We made it diabetic, type 1 diabetic, so it had high glucose levels and nephropathy. And the idea was that, and this was going around, a study going around at the time, Rob and Jerry Wilkins were interested in the renal denervation proposal, and there were some small clinical trials at the time, but no real definition. We took these rats, burnt off the nerves going to and from the kidney to the brain, so we severed that connection, and as a consequence, the damaged kidney that resulted in the diabetic nephropathy was not affected, so it was not able to relay messages to the brain. Neither could the brain then increase sympathetic tone to vasculature or to the kidney. Long story short, if you look at this at the top, And we've got Yimin Yao and Ingrid, pharmacist nurse, and Jed Davis and Rob and Joanne over here in this. And if you denervate the normoglycemic, the non-diabetic animals, you get a drop in blood pressure. If you denervate the diabetic innervate animals, you had a more profound drop in blood pressure. These are already quite elevated. The systolic blood pressure went up to 220. So it's pretty high. The other thing I have to say is that human had to denervate these arteries, God, there had to be a word, every 3 weeks. So just to make sure they didn't grow back. Human is now, not surprisingly, well away from renal nerves. He's a senior scientist at a company in Sydney and doing very well. Just to bring you up to clinical significance, the European Society of Hypertension has advocated renal denervation as a class 2 recommendation now, and they've given approval for patients with uncontrolled hypertension. The FDA has given approval for 2 devices, and one of them is the Simplicity device, the other one is the Paragon device. The idea is that, Paradise device now, is that they produce symmetrical burns through the internal renal artery. You don't have to open the patient and tear the renal nerves off. You just burn them using radio waves or ultrasound. So that's great. We also looked at the importance of cardiomyopathy in status epilepticus, and it's, this was work that we wanted to focus on. It started off as a wager between Steve Carr and myself. Some of you remember Steve here. I don't know, he's not here tonight, is he? Good, right, great. So Steve didn't believe anything south of the brain existed. I pointed out to him that the heart and kidney were very much under CNS control, and if you had recurring seizures, you could produce damage to the heart resulting from the tachycardia that resulted. So if you look at status epilepticus, it's a major worry in patients with severe seizure, and it can lead to cardiac arrhythmias, mainly because it causes these substrates for arrhythmias to form, this arrhythmia formation over here. And you can see this blue fibrotic stain with inflammatory cells in here. So this is one we prepared earlier, if you like. There's a lot of apoptotic cells and so on. So this was a model that Steve had developed. We put telemeters into these animals, measured ECG and EEG simultaneously, and Morgaine was responsible for doing most of this work. And we've got, we confirmed cardiac injury in there, and then we went to look at the pharmacological interventions. Where it becomes important to the title is the whole component of broken heart. Okay, so broken heart is a form of heart failure, if you like. It is important you recognize this in that we have a sympathetic storm, either produced by the seizure itself or by the by stress, by grief, by sometimes illicit drugs. You get this release of catecholamines that pour onto the heart and produce these adverse events that result in these ECG changes and changes in the wall structure. So much so, to cut a long story short, in some patients you see arrhythmias and death. In some patients, Takotsubo-like syndrome is produced, where you've got this ballooning of the ventricle. Now it's called Takotsubo because the Japanese clinicians that noted the resemblance to this octopus pot over here. So fishermen use this. They put a pot on the bottom of the ocean, and octopus climb into it and they pull it up. Shape looks like this pot over here. And in a small percentage of cases with severe seizure, you can get this development. So we thought if you've got a large release of catecholamines, what better than to try and block it using beta blockers or else to use clonidine to prevent outflow, or else calcium channel blockers to protect the heart. And Morgaine and Rebecca Millen and Dominic Perry, was Morgaine. I really appreciate the work, so I'm giving you a photograph over here that you enjoyed. They show that if you put atenolol in, it offers better protection than clonidine in reducing status epilepticus. But what was also more important in a head-to-head study, we looked at atenolol and diazepam, which is a traditional drug used for status epilepticus, and atenolol in combination with diazepam produce cardiac protection. So the net result is, and I'm not putting this all down to us, but if you say that now there's a significant amount of attention being poured onto status epilepticus and cardiac injury and to Takotsubo syndrome, beta blockers are now regarded as really promising agents. So are ACE inhibitors as well. Okay, so back to carbon monoxide. We'd left it alone mainly because of all the issues I raised about CO gas being toxic, right? Why would you want to give this to a patient? Well, if you use CO gas by inhalation, there's a lot of issues. It's unwieldy. You've got to get it across the respiratory airways. It's got to, as Matt Bevan will tell you, cross into the circulation and then get to the mitochondria at some distant point in your small toe. So you've got a dilution effect as you go through. The really important thing over here is that we wanted to find a better way of doing this, and my old collaborator, Roberto Martellini, focused at that time on the metallocorms and on the boron hydrate compounds. And I don't want to do him a disservice, but these compounds have carbon monoxide independent effects as well. So it's not just CO that's having the effect, the compounds themselves have. And you look at the structures, some of you may recognize ruthenium in there, and ruthenium is a cytotoxic agent. Okay. The effect, the release is unpredictable. Some of the researchers hadn't used positive CO gas controls, and this is where we then looked at the implications. So Joanne and Ian Wimburn, who was a PhD, a surgical registrar doing a PhD at the time, studied these compounds on cardiomyocytes, both freshly isolated cardiomyocytes and on cell lines, and showed that the carbon monoxide itself didn't have any toxic effect, but the ruthenium sure had. So the accumulation of the inactive corm, the one that had released the CO, proved cytotoxic, and we considered that to be a good paper to submit. It was published well. The authors of the previous papers weren't too happy with us because we had shown a negative result to their stuff. But if you're interested, Bingyi Wang, who's a visiting researcher coming here next week on Monday, he'll be talking about carbon monoxide donors, and he also has disproved the quality of those corms. So there's a number of publications now reinforcing negative effects. So let me just remind Rob of the time we spent trying to get Ian to publish up his thesis and his paper and so on. So Ian left with a skip and a jump, and he really was a nice bloke, very intelligent, but he left and then went to the UK, re-entered surgery, and decided that surgery wasn't going to be ideal for him. So having told me he never wanted to write another paper in his life or write another thesis, he's now the global director for Pfizer's medical, sorry, it's a long title, I've forgotten. But yeah, basically he's earning more money than I am. Right. Okay, so so we got funding, and this was largely due to Joanne, who brought in Heart Foundation money with me, and I'm the pillow slips on the MB grant, as David Larson said, so it became a very sound grant application. I'm grateful to you for that. David Lawson had come up with this structure where if you put these compounds, these organic carbon monoxide releasing molecules, into a pH buffer, which is a physiological pH of 7.4, this halide leaving group over here would come off, and the bridge carbonyl compound, if I can get this right over here, breaks down to release carbon monoxide. And it does so it releases the spent byproduct and releases carbon monoxide. And this is where Margaret Brimble was involved as well. So yeah, there's a few people on this. At that point, we got this most premier journal in New Zealand saying that exhaust gases could benefit heart patients. So we've got a Heart Foundation grant at the same time, and I still have to get the idea that you can stand behind the car and protect yourself into my head. Okay, so quick trips through some points. One is that we show that if you look at the orange blocks over here, it shows the byproduct forming within a set time. This is true mass spec analysis, and the byproduct, the OCHM21 itself, deteriorated, and we got an idea of the half-life of the drug. So it was about somewhere in the region of 15 to 18 minutes. No cytotoxicity. We expose these drugs, cells to these drugs, and we used a variety of cells, not just cardiac cells, but kidney cells and so on. So there was no cytotoxicity. We did this for 1 hour. We extended it to 24 hours or even 48 hours, well beyond the expected accumulation time. You did get some cytotoxicity, but it was above the pharmacological dose. So then I and Joanne looked at whether the carbon monoxide was getting to cells, and Leslie Lawson, bless her, Dave Lawson's wife, got a Bo-Dippy compound for us, and we loaded it into the cells, and it fluoresced when it came into contact with carbon monoxide. So we preloaded it, put the CO into solution, the CO gas got into the cell, and we got definition that it was in there. If you look at this much higher concentration over here of BP21, the cells are still there, but there's no carbon monoxide in any great quantities getting in there. Remember, these cells still have homogenase and still produce carbon monoxide. The chemistry team also produced this fluorescent molecule that, when it broke down, would fluoresce in the blue. The red here would be a mitochondrial trachytide that depends upon the membrane potential of mitochondria. So fluoresces nicely over there. You put the CO donor in, and by 18 minutes later, it's built up in the cells and fluorescing in the green now with Bo-Dippy, and then it releases and the carbon monoxide gas comes off. The blue phenanthroline compound, if I recall my chemistry correctly, cells fluoresce in the blue, so the breakdown product is in the cell, and the red comes back. These are all fused together in terms of images, and you've got mitochondrial function returning. Rachel Hartley was a third-year med student at the time when she did this work, and that led to a publication over here with Rachel on it, and others as well that were involved in this. In chemistry, had produced other work as well with these compounds that were vital to our requirements. So small step back to carbon monoxide in kidney transplants. Now we want to see if the OCHMs could protect the hearts, and yes, we got increased vasoresponsiveness. So if we use the gold standard University of Wisconsin as a control and look at flow rates and resistance, we increase flow rates slightly, but not significantly. This was at 8 degrees, okay? Most tissues don't function greatly at this temperature. But the resistance in the vessels went down. So we've got an improved perfusion. And if you think about it, when you take an organ, very much like the ones you put in the fridge, okay, and you store them, when they come out, they all look blotchy, and that's because there's poor perfusion through the organs. And that's the problem with transplanted organs. We have to be careful when we reperfuse them. So the idea was to put in a UW solution that would prolong the life expectancy of the organ storage. It would allow us time. This is a LifePort machine. It will allow clinicians or scientists time to actually start putting gene vectors in there and manipulating the structure of the kidney and adapting its ability to be accepted by the recipient as well. And here's one for the med students in the audience. When you add angiotensin II, you should get an increase in the vasoconstriction in the efferent arterioles, okay, and resistance builds up. And in kidneys that are stored at 8 degrees, you've got this level, but when you add the Ockham donor, you get improved responsiveness to angiotensin II, showing that angiotensin II actually has the ability to improve the pharmacodynamic responsiveness to vasoconstrictors even at 8 degrees. Okay. We also show that these drugs are vasodilators, very much as the stuff I've done in the British Journal of Pharmacology paper. Ockham-21 proved the most potent agent. We could reverse it using guanylate cyclase inhibitors that confirmed that guanylate cyclase was important vasodilation. So the idea is to get carbon monoxide into cells and around key signaling molecules or signaling pathways like guanylate cyclase. We don't want it in the circulation. We want it to get into cells where it can have its effect and not a toxic one. So a few more slides, and I promise you I will finish soon. When we pre-treated hearts with a vehicle control, so in other words, untreated, okay, and you can see the left ventricular developed pressure measured by putting a balloon in the left ventricle. We expose those hearts to ischemia, and the results after 30 minutes of ischemia and 60 minutes of reperfusion, where we re-administered blood flow, well, in this case, perfusate flow into the hearts, we got little left ventricular developed pressure forming. If you pre-treat the hearts with Ockham-21, it did two things. One is increase the force of contraction in these hearts, and I'll show you that in a second, but it also produced a greater development of pressure between the period where the heart is contracting at its peak and when it's relaxing to its minimum level. So in other words, the blood, so the ventricle of the heart can accommodate more blood in that period. And that's shown in this graph over here. So we've got significance being shown over here. Okay, we got the drugs patented. That's great. Took a while to get that done, but it was really useful. And it's, as Richard said, we've had this patented in a number of different countries now, thanks to the efforts of David Christensen and the oil team. We also got an HRC grant to look at this in 2020, and it had two aims to it. One is, could we protect hearts in advance of an ischemic, a known ischemic episode in, say, off-pump bypass? I'll explain that briefly in a second. And the other one is to do this in an on-pump bypass, which requires a lot of perfusion pumps. Yes, we can do this in a rat, but why do it in a rat when you can do it in a sheep, yeah? Okay, so sheep have got larger blood vessels, easier to cannulate. We're working on this, and sorry, Dave, the Wellington BRU faces a major problem because we have a lack of a building over there at the moment we can use. So we were asking the HRC yet for another extension. But Steph Thwaite had done most of the work on these isolated hearts, and it was built up on work that Rob and Jerry and I had looked at in previous studies, but Steph, although, and she's not here today, so I can say this safely without her smacking me, she can be a very demanding PhD student, and she was, but she is an excellent surgeon. She had done a lot of this work in hearts that were exposed to sham ligation, where there's no occlusion or treated. So let me tell you about that. So if you take this off-pump bypass in a patient, the heart is rotated so that the surgeon's got access to the coronary arteries that they need to bypass to put a blood vessel around. For that, you need a stable field. So you need a positioning arm over here to hold the heart steady, but at the same time, you need to have this clamp that's put around the coronary arteries that are going to be sutured. That stretching of the ventricle and positioning and twisting also produces an ischemic episode. So we knew it was going to happen. And what Steph did was model that by putting a ligature around a major coronary artery, producing the same level of ischemic injury, and then reperfusing it, same as would happen when you release these clamps. So the drugs, the OCHMs, 54, 21, had no effect on the heart when there was no ischemia, but when you put into the coronary ligated mode, now there's ischemia, you've got this massive increase in this biomarker of cardiac injury. This is cardiac troponin I, it's a clinical marker. OCHM 54 brought it down, but OCHM 21 reduced this to the same level as baseline. So the drug works. We've got a lot of other data. Sean's looking at the echo data as well in this. And there's a number of things we still need to complete. But there's a lot of histology that's confirmative, and Joanne's done the immunolabeling on it as well. So, a couple last things. One is we also looked at whether OCHM 21 can increase the force of contraction, but also increase calcium sensitivity. And this work was done by Fergus Payne, who's just left for a postdoctoral position at the HRI in Sydney. So he showed that OCHM 21, 10 micromolars, push this curve to the left, so increasing the sensitivity of these isolated myofilaments to calcium. By the way, I should say that this is a cardiac myocyte. It's been attached to a transducer and to an anchor over here. This is work that Chris Baldy and Gary Duffy had brought in, and I'm very grateful to them because it showed that OCHM 21 increased the calcium sensitivity of the myofilament. We also did this with carbon monoxide gas at the same concentration, and the red line shows exactly the same effect. Jerry Wilkins was also involved in this work, and I'm grateful for his insights. What we did see is that if you took the hearts and exposed them to the OCHM 21 at 3 in the blue and 10 micromolar, you got an increase in the left ventricular developed pressure, so it increased the force of contraction. So this is a positive inotrope and suggests that the drug can be useful in increasing pressor responses, increasing the force of ventricular outflow following surgery, and much safer too. So I'm going to finish with this slide. So this is going back to my therapeutic teaching. I'm pretty passionate about pharmacology, as some of you would know. Can't think why, but we've got a wealth of researchers over here and a wealth of good teachers. The last thing I want to do is see pharmacology being diluted in the medical program. I want to see it being built up. I want to see it remain at the heart of the way we train our students. Why? Because you will see, and I have seen, patients being prescribed badly. Let me put it this way. There are situations where patients should have been better monitored for drugs that have been given, taking into account their kidney function, their heart, cardiac function, and so on, doesn't always happen very well. So we need to make sure that our teaching remains up to date. Our lecturers, our experience in this delivery, we should use more case-based demonstrations, so we need to have time within the medical program to do that. Giving a dry lecture isn't always the best way of teaching. Reinforcing clear messaging and prescribing, that has to be done at levels not just within the ELM or ALM, but even above, and using research and practice-based informed teaching. And the last thing I'm going to say is we have good pharmacologists, good pharmacy people, pharmacoepidemiologists and pharmacovigilance people here. Okay, there's a lot of pharm in the titles. We all do different things, but we should be working together to produce a better outcome for our students and our clinicians in their training. So I'm going to stop with a couple of last slides. One is, these are the acknowledgements for all the people who have worked with us. This is mostly New Zealand teams, all the people that have supported us, and I'm very grateful to all of them for the work they do, and some of the, even some of the people that have made me pull my hair out. And I've said that it's third year ELM as well. But, so I'm going to thank my family, and by that I also include not just my wife and my children. Thank you, Laura, for attending. But as you know, Jock is in my will. That's my dog over here. He keeps me happy. He's always there when I come home. My students and researchers who have stretched me as much as possible in a good way. My mentors here in the UK, my colleagues, my department staff, thank you very much for all your support. And last word, and that is, I got really excited when I saw this little yellow digger coming towards the Adams building, and I hoped that it would spell the end. Unfortunately, it didn't happen. So, okay, so I'll leave that with the funders. Thank you very much.
I think we've just got the department is gathering. Thank you, Mrs. Maybe it's Heart Otago that's gathering.
Did you get the rest of Heart Otago because the sync was better?
Sorry, I did the wrong thing. So normally it's the head of the department that gives the vote of thanks, but as Ivan's the head of department and everyone else is sick, last man standing was me. So so Ivan, please help out, because I think I might need your help with the thanks. So I think we've really seen a great lecture tonight with Ivan's passion clearly on display. I think if such enthusiasm and real focus on clinical outcomes has really been a highlight to see that. And I think we've seen a journey of Ivan coming from Sunderland to London and then on to here, and all started by the heart on his grandfather's desk. But I really don't think he's moved very far from that heart. I think it's come along with him, perhaps. So even though he didn't go into the medical career that some in his family perhaps wanted, it seems like he's not really moved very far. And so they should be very proud of you. And I think, I guess, tonight we've seen a real emphasis on the close connection between clinicians and research scientists, and then the involvement of graduate students, whether they be science-based or clinical graduate students. And I think it's really sums up a university really nicely, how everything comes together and really can make a difference. So it's a really nice academic journey, and I guess highlighting the impact of translational science. And we've seen from carbon monoxide to MitoQ to OCOM. I was a little bit losing track of some of the different things, but always at connecting them all up was a real clinical focus. So thank you very much, Ivan. It's my job to shake your hand. So thank you.
Thank you. Thanks very much. Thank you.
So I really think that we'll need you to come and do another instalment in 5 or 10 years. We want to see where things have gone in the next part of the journey. And I'll pass over to Richard.
Thank you.
Well, what an evening. What an evening. Thank you very much again. And thank you, Catherine, for filling in so many roles at short notice. Congratulations again, Ivan. It is my duty to say thank you for your attendance. Haere rā koutou. So farewell this evening to you all, to those here and online, but also on behalf of the Pro-Vice Chancellor of the Division of Health Sciences to invite you for refreshments. No lecture is complete without some really in-depth discussion and sharing of kai and drinks and fellowship and exploring the subject matters in more detail. So please, let's thank Ivan again and join us all at the Staff Club for refreshments. Thank you very much.
Thank you very much.